It's the fundamental theorem of algebra that says if you have some kind of quadratic, I'll just say bx plus c, that it can be factored into linear factors, two of them, where these p and q might be imaginary numbers, complex numbers, or rational. And the same thing is true for like a cubic. It can be factored into three linear factors, where the p, q, and the r might have some imaginary complex numbers involved in them. So if you have a cubic, for instance, x cubed plus 4x squared plus x minus 26, and since this 1's here, it's going to be integer. If there's a real root, it's going to be either plus or minus 1 to 13 or 26. And if we actually go ahead and start testing values, we would find that for x equals 2, or for the factor x minus 2, it would work 13, 0. So this thing would factor to x minus 2 times x squared plus 6x plus 13. Now, though this x squared plus 6x plus 13 isn't something that you could really like factor nicely, if we run it through the quadratic formula, x equals negative 6 plus or minus the square root of b squared, which is 36, minus 4ac, which is minus 52, over 2. X equals negative 6 plus or minus the square root of negative 16 over 2. X equals negative 6 plus or minus 4i over 2. X equals negative 3 plus or minus 2i. Now, when you have an equation like x squared minus 5x plus 6 equals 0, and it has two roots, x equals 2 or x equals 3, which we got usually by factoring. So the factors are x minus 2 and x minus 3, and the roots are x equals 2 and x equals 3. Going the other direction, if I know the roots are x equals 2 and x equals 3, that would mean the factors are x minus 2 and x minus 3. Here I have roots, pretend there's like an equals 0 after that. It has roots here, which means the factors would be x minus each of the roots. So x minus 3 plus 2i and x minus 3 minus 2i. That's how I'd write that out. So I factored the cubic into three linear factors. Here's a fourth degree. 2x to the fourth minus 1x to the third plus 5x squared minus 4x minus 12. So there's a 2 here, minus 12 here. So the roots come from 1, 2, 3, 4, 6, 12. That's a lot of stuff. And 1 and 2 on the bottom. So a lot of possibilities. Imagine you tested some of them, and it's going to jump ahead, and you got lucky and tried negative 1, 2 minus 1, 5 minus 4 minus 12. You would get 2 minus 3. Negative 1 times minus 3 is 3, plus 5 is 8. Minus 1 times 8 is negative 8. That's minus 12. Gives me a 0 there. So this thing would factor into x plus 1 times 2x cubed minus 3x squared plus 9x. Plus 8x minus 12. Now I kind of have to start over with this guy. It's basically the same list because I still have a 12 and a 2 here. I'm not going to go through the process because that was from the last video, but let's say that you eventually got to the point where you were testing 3 over 2. You would get 0 here. You would get 8 here. 8 times 3 over 2 is 12. You get 0 there. So that would mean that this 2x cubed thing could be factored into into x minus 3 halves times 2x squared plus 8. Factor the 2 out of here and give it to this guy. It turns into x plus 1 times 2x minus 3 times x squared plus 4. Now I don't need the quadratic formula. I could just kind of solve when does x squared plus 4 equal 0, when x squared equals negative 4, when x equals square root of negative 4 plus or minus, or when x equals plus or minus 2i. So that means that this polynomial is x plus 1, 2x minus 3, and I'll write this, kind of factor it as x minus 2i and x plus 2i. And that's how you can do what we've been doing with factoring, but we can keep going even when the quadratics don't seem to factor. We could either use the quadratic formula to get the 2 roots, which then give us the 2 factors, or sometimes we don't even need the quadratic formula because there's no linear term.